Hi everyone. Okay, today is yet another JC video that I'm recording. So the first one that I did was on mathematics, and in today's lesson we're going to talk about a subject that some of you may be taking and is also really struggling, okay, which is on physics forces. Okay, this is one of the very fundamental things that you need to learn in physics, because thereafter almost every topic you will also need a little bit of this. Yeah, so you think about, for those who are in J2, you learn about motion in circle, then you learn about simple harmonic motion, okay, oscillation, then after which you talk about the different fields, gravitational field, electric field, so on and so forth. So somehow or rather, when you deal with force, then knowing how to do or treat the force part, it becomes something that's really, really important. Yeah. So, but of course, this actually is just the fundamental to help you to tackle of how to resolve the force, how to get the force that you need to actually get the quantity that you want. So that's why this is a very fundamental yet very important topic that you have to learn in JC. Okay, so when we talk about forces, right, I think the first thing that you must be able to know is you look at the diagram, what are the forces that you are actually looking at. So this is really important. And take note that when we are dealing with solving a question, right, most of the time you also must be able to differentiate between this force is acting on A or B. Is this the correct object I'm looking at? Because you understand the concept of free body diagram, it must be only on the object of concern. Alright, so like in this case, when we talk about the first diagram, there is this force called tension. The thing that comes to our mind when there's tensional force is because that there's actually string attached. String attached will actually provide a force on the object called tension. And take note that tension is a force that is always acting away. So in this case, if let's say this is the object I'm trying to lift, the tensional force will be in this direction. Or you can follow the blue color arrow that's already there. Okay, second thing will be this thing called the spring force, which you also learn in JC. So spring is also a common thing that you use, but in the past you have never learned how to calculate the force due to the spring. And in actual fact, spring is an elastic object, so the amount you stretch or the amount you compress really going to affect the spring force itself. And of course, second to that will be, what spring are we looking at? Is the spring a stiff one, S-I-S-T-I-F-F, or not so stiff one? So the stiffness is going to affect this thing called the spring constant, K. It's a coefficient that you multiply to an X in order to get the force. Okay, so this is the second very common force that you get to see. And third one will be this thing called reaction forces. Okay, take note that I'm not talking about just normal reaction, but reaction force in general. And you look at the diagram I've given here, the first one is talking about this thing called the normal reaction force. So normal to what? Normal means 90 degrees. Normal means it is perpendicular to the surface that you are on. This part. Okay, this is the surface, 90 degrees to it. So this force is in this direction. And this will always happen when you put object resting on the surface. There will always be a normal reaction force. Reaction because it's reacting to what you are doing to the surface. So when you put an object on the surface, you are actually exerting a force on the surface. So it's reacting, pushing you back against it. And this force, take note, is reacting to the weight of the object. So in this case, it's trying to support the weight. Okay, second reaction force that you often see, but you might not know is a reaction force, is called friction. Friction is also a reaction force because when your object is moving up the slope, the surface will provide, if it's a rough surface, it will provide a force that's acting against it. So this is a frictional force, and because you're trying to go up, so I'm trying to go against you, so it's a reaction force. In fact, actually, don't know whether you know that you rest an object on the table, horizontal table, do you know there's no friction? Yeah, because you haven't tried to push it. Remember, friction is a reaction force. So if you did not try to push it, then there won't be any reaction force, because it's supposed to react to what you are doing. You did not try to do anything, why would I react to you? Okay, so this is the idea of the types of force. Okay, coming to the next key important point. Okay, there's of course many other forces that you need to know. So if you want to know more, you can actually contact me, give me a comment. I will share with you more. But I think those are the key ones that you really get to see in the question. Okay, the next one is talking about equilibrium. So in this topic of force that you're going to learn, right, the key focus is talking about this thing called static equilibrium. If you recall from the lesson in school that static equilibrium is talking about an object in a state of static means not moving. So not moving, and the things that's acting on it is balanced. Okay, so not moving plus balance means your object is not going to move. And of course, the other one is called dynamic equilibrium. Dynamic equilibrium is the one that you learn under the Newton's laws of motion, where you talk about an object can be traveling at a constant speed, like your car. You drive a car, then travel at a constant speed, then in this case it's dynamic equilibrium. Because the forces acting on it is also balanced, which give people an idea that, oh, that means to say my car is not supposed to move? No lah, the car will still move. Just that the car will not accelerate because the forces are balanced. Okay, so but in this topic, we're going to go further into talking about the two types of equilibrium as well. So not just static dynamic, but rather if you just say it's static, it can also be static due to the forces are balanced, called translational equilibrium. To help you to understand what is translational equilibrium, right? Imagine if you have a box that is resting on the table, your friend tried to push in this direction 10 Newton. For some reason, you are very naughty. You want to push in the opposite direction, also 10 Newton. So the end result, nobody will win. The thing will move? No, the thing will move. The thing will remain at rest. Because you are in translational equilibrium. Translate means you shift left, right, up, down. Straight line motion. Okay, most of the time it's straight line motion. So translational equilibrium means all the forces are balanced, and if it's static, then static equilibrium, then it means to say that it will not move. Okay, nobody will win. Then the other one is called rotational equilibrium. This one is really pertaining to what we call rigid body. And let me relate to you that in O-level, you did learn about rigid body, but you might not call it rigid body. You call them beam. So the common diagram you see in O-level in the past is a beam with a triangle. So it's like a lever kind of scenario. So this is a rigid body because this body has a sizable length. Okay, maybe some thickness as well, but main thing is the length. And if you apply the force, the location where you apply the force will actually affect the object. You move the object, but not a translation sense, but rather it's a rotation sense, especially if you have this thing called a pivot. Correct? Remember? Right, pivot, so it will rotate. So this is a rigid body. It only applies to object with a certain size and length. So which is relevant relative to the rest of its surrounding, right? It's long, it's large, then we call it rigid body. Then we have to consider where the force is applied, which will affect the object whether it will rotate or not. So we talk about this concept called rotational equilibrium. Of course, there's a graphical way to treat this translational equilibrium and rotational equilibrium, but I'm not going to talk about it here. I'm going to focus on the part of calculating only, right? But just to share a little bit, translational equilibrium, you can use a equilibrium triangle. Or what we call the closed polygon method. So if I draw the forces, everything by scale, then I'm able to form a closed triangle or closed polygon, then the thing must be in equilibrium. Then on the other hand, rotational equilibrium will be if all of them pass through a common point, all the force pass through a common point, like for example like that. Then if I take pivot at this point, the moment will be zero, so you have no net moment. Okay, so this is a two-way to consider the translational and rotational equilibrium using your vector diagram or the force diagram. But today's lesson, let's just focus on the calculation bit. Okay, and of course, to begin the discussion now, we want to talk about how we can solve for an unknown force in your question. So the first thing that you need to be doing is to draw a free body diagram. Honestly, you look at these few pictures over here, right? The first one on the left, right? This one. Okay, wait, let me change my color first. You can see this picture on the left. This picture on the left is, if I ask you what are the forces involved, you probably will think a while, then you pause a while and you try to figure out what's going on. Because in real life, we're going to see things like this. And to understand what exactly is going on, usually it's hard. Yeah, because there's so many things connected and all. So in this police system, right, probably it's a bit hard to understand what's going on. So likewise, if you look at the next one on the right, similarly the case, but at least this one is a 2D diagram. 3D diagram, there's many more possibility. So you want to draw the 3D diagram or use a 3D picture to try to understand what's going on is usually hard. And 2D diagram, a bit better, at least it's 2 dimension, but the best would be the one at the bottom, which is this one. So this is a common question in the kind of exam scenario. Pulley system, 2 block, one on the slope, one is actually resting freely on the other hanging surface. Yeah, so things like this. But even that is not useful enough to help you to figure out what's going on, because we really need to just isolate and look at one of the object. But just that in JC, it's also possible for you to not isolate just one object. You can also isolate this as a system as a whole. Okay, so you can actually do either or. But of course, if you're going to do the whole thing, the whole stretch of thing, with 2 blocks as one object and then the string is connecting them, then please remember, do not consider the force on the string. This part, okay, there's tension, right? They become internal forces and you should not consider on your free body diagram. So meaning to say that the free body diagram, right, will just be one box, one string, one box, then there's a weight here, there's a weight here, full stop. Do not consider the force on the on the string itself, because those are internal. Okay, internal means it will not affect the net force and all these things if you look at it as a whole. But if you look at the box individually, then you have to remember to consider the tension. There's a lot of science to that, but at this point I will just go through the main point. Then after that, if you are interested to learn more, I'm always happy to share. Okay, now, so when you want to talk about solving the problem, the first thing will be to draw the free body diagram. So in this case, imagine this is your question. So to draw the free body diagram, right, maybe I focus on the block. Okay, so I can actually focus on the beam as well. Okay, there's a rod. So this rod, there's a tensional force acting here. So let's call this T. There's a weight uniform, right? Uniform means the weight will be acting in the center. Then this is the pivot P. Okay, if let's say you want to find out the forces acting at the hinge, the P, right? By right, you are supposed to draw this as well, and up and to the right. So this is Ry and this is Rx. So Ry, Rx actually means the reaction force acting at P. But since I do not know whether the force is up or down, left or right, I make an assumption first. So the convenient way will be, imagine it's up and to the right. Okay, that's your Rx and Ry. And that's about it. That's the free body diagram of the rod. Then after which, you can also look at the block on the right hand side. So the block on the right hand side will just be having 2 forces. 1, the weight force. 2, the tensional force that's connecting between the uniform rod and the 3 kg object. And that's all. Okay, that's all. Right? So these are the 2 objects free body diagram. And if the question say that the object is in static equilibrium, nothing moves, then I will say that T must be equals to weight. Okay, so the balancing of force and moment part, which is our point number 2, is exactly what I'm doing here. But for the case of the 3 kg block, we don't expect it will be spinning and rotating. But however, the beam, because it's long, so by right I will be able to discuss possibility of it rotating and whatnot, because it's acting at the distance away from pivot P. So for that, right, because of that, we need to balance out the moment. And in this case, the convenient point to take the pivot about, right, will have to be at P. So if let's say this entire thing is of a length L, then I can say that maybe I will have a clockwise moment first. So clockwise equals to counterclockwise, right? So the weight will give a clockwise moment, and in this case, it will be W times L over 2. So this is P as pivot. You must always in the question tell people where is your pivot. Okay, so P as pivot, convenient. Then after which, right, this clockwise moment should be balanced out by the anti-clockwise moment, which is from the T. So for the T part, right, take note, you cannot just put T times L, which is the entire length, right? Rightfully, you need to do a bit of force resolution. So on the right side, right, okay, sorry, okay, so this I will break it up into, this is T sine 36 degree, this is T cos 36 degree, this is my T. So I will say T sine 36 degree multiplied by L, the entire length, because take note that the force must be perpendicular to the length to find moment. If not perpendicular, make it perpendicular. You don't have to do this in O level, but you definitely need to know how to do this in A level. Okay, make sure the force is perpendicular to this distance, right, before you calculate the moment. Okay, so this is actually how to balance the moment. So we talk about the balancing of force and balancing of moment, and these are just creating equations to solve. Solve for what? Solve for the things that you want to find. So if this thing is in equilibrium, the forces all add up together should be balanced. Then the forces, the clockwise moment, anti-clockwise moment should be balanced as well. But as for the system, you can choose to look at either the 3.6 3 kg object or the beam itself, or you can look at them together. So it depends on how you want to do it. So sometimes you find that just looking at the plot itself is not sufficient, look at the beam itself not sufficient, then you can look at them together. That might be easier. Okay, so this is the two, I think, very important key point about solving a question like that. Okay, now let's finally look at an actual real life exam question that you might encounter. So this might be a bit long. I will try to do it as fast as possible, but go through the steps. So I may not work out every single number, but the main thing, I want you to understand the process. So focus on understanding what are my processes. I'll label the step very clearly for you. So eventually, if you're going to do it the next time round, look at the question, please try to follow the steps. Okay, so this question is talking about a beam, okay, a uniform bar, 5 meters long, never mark out for you, but 500 Newton uniform, which also means to say that CG at 2.5 meter, right? Okay, I will immediately process this information. The CG is at the midway point, supported by a wire. Determine the magnitude and direction of the reaction force from the wall acting on the bar. So the first thing I will need to figure out is, what are the forces acting on this bar, right? So maybe we can begin by number 1, draw FBD. Draw the free body diagram. Okay, so I will draw a very simple one, no need too complicated, just a line like that. Okay, what are the force acting? I have 1 here, this is tension T. I have 1 here, this is my weight W. And of course, last but not least, at the end, I have 2 forces, Ry and Rx. Once again, take note that I do not know what exactly is my Rx, Ry direction, so I'm just going to leave it as up and right for convenience sake. Okay, I might be wrong. Okay, sorry, let me clean up the diagram a bit first. Got some extra line, okay, like that. Okay, so Rx, Ry, this is your assumed direction. If let's say you get a negative answer for either one of it, please remember negative means you have to turn the arrow around. So if Rx is negative 2, so sorry, it's not up, it's down. Okay, remember to turn it around, but we'll talk about that later. So eventually finding out what is Rx, Ry. Okay, but at this point, you realize that we also don't know what is T. I don't know what is my tension. So that is the first thing we're going to do. Okay, and to make it happen, basically we need to resolve the tensional force first. So after you draw a free body diagram, right, you might want to think about, should I add up the force equal to 0? Or should I add up the moment to be equal to 0? And I will not do the moment thing, I won't do the force thing first. Cannot add up the force, because take note that I have a total of 3 force that I got no idea what are they. Tension don't know, Rx don't know, Ry also don't know. So my suggestion is that you take moment first. So let's say this is the pivot. Okay, then this tension, right, we resolve the tension along the beam. That should be the easiest. Okay, so if I resolve along the beam, I have an angle, so it's easier that way. So if this is 20, then this is the part where I will say this is T sine 20 degree. Then this part will be T cos 20 degree. Take note that T cos 20 degree, as you continue to travel upward, right? Do you notice that it will pass through the pivot? Okay, let me try to draw for you. So there will be no moment from T cos 20. So now, after we have figured out all these things already, let's try to find T first. So how will it look like? Clockwise equals to counterclockwise. So number 2, CW equals to ACW. Okay, take note that step 2, right, can also be upward force equals to downward force. But like I said, right, it's provided that you have enough information about all the forces. If not, then please use moment, because when I take pivot about the edge, right, I can basically ignore Rx, Ry, because they will not be generating a moment, no perpendicular distance. Okay, so now, the clockwise moment will be due to the weight, right? So the weight 500, 500 multiplied by, what's my perpendicular distance? Okay, you draw a dotted line. Then this part is the perpendicular distance. Okay, what is the angle of these things? It's 60 here, right? So this will be 30 degree. So I'm going to use 30 here, 30 degree. And this length here is 2.5 meter. How do I know? The entire thing is 5. Uniform beam, the weight will be acting in the midpoint. So 2.5 along here. Then that means to say, if I use Duacaso, I wanted to find the perpendicular distance, which is the bottom part, right? So it will be this part. So this part using Duacaso, it will be cosine. Okay, so I'm going to do 2.5 cosine 30 degree. Okay, 2.5 cosine 30 degree. Then from here, okay, we can then equate to the anti-clockwise moment, which is due to the tension. So this will be this one only, T sine 20 degree multiplied by 5. Why 5? Because the perpendicular distance, this is perpendicular to the entire beam. So we'll multiply by 5. Okay, then after which, you can then use this to find your tension T. Okay, not going to solve it, but you can actually solve it yourself, the tension T. Moving on to the next step. Okay, now, I know about the tension already. So now we look at the next diagram. Okay, so tension T is here. This is my T. Okay, and I know my weight as well. The weight is here. The point is we want to find this Ry and this Rx. Okay, you want to find these two forces. And these are all the forces acting on the beam. Alright, so in order to make use of the diagram to help you to find what you need right now, I need to make everything to go resolve all forces vertically and horizontally. Because then you can do the adding up equals to 0 thing. So for the vertical part, I have Ry plus T, the tension has an upward component, right? So if I resolve this like that, this will be T. Okay, this angle here is actually 30 degree because it's 60, right? Right angle triangle, 60, 30, that's 30. Total will be 50. So this will be T. The particular one will be T sine 50. Then this T cos 50. Correct? So the up one will be T sine 50. And these two upward force will be equals to the weight. Okay, so which is equals to the weight. Okay, and take note that you don't know Ry, you know T already, you know W already, so you can then use this to find Ry. After you find Ry already, let's move on to Rx now. Rx is much easier because I only get Rx, one horizontal force to the right, which must be balanced by the tension force T cosine 50. Then you you find your Rx. So Rx, Ry both find already. Let's say they are actually in the positive direction. So they are up and right. I did not make a mistake. Then finally, step number 4 will be you use your Pythagoras theorem. So I'm going to put Rx here, Ry here, put them together. Then you use a vector triangle to find your total R. So Pythagoras theorem will be R equals to the square root of Rx squared plus Ry squared. And then you can find the magnitude. The question also asks for the angle. Okay, take note. So you can use tangent to help you. Let's say this is your theta, right? So tangent theta is equals to Ry over Rx. Then you will be able to find the angle with respect to the horizontal. Okay, so this is the last step. And the thing that I want you to learn from this video, number 1, is the steps that I went through to get the value. Usually a question that is kind to you, when I say kind, because they will guide you all the way. They give you part A, part B, part C. So take note that all this part is meant to help you to get all the different quantity that you need, eventually leading to this correct answer. And in this actual question, what I did was I actually removed one part of it, which is the finding of tension. So a guided question will ask you to find the tension first, which I need anyway, then before you move on to part B to find the reaction force. But even if they did not tell you in this direct manner, right, please also think about it that most of the time the previous part should be able to help you to get the answers. And of course, at the end, right, you can see that in doing a question like that, you need to be able to exercise the way you resolve forces. Is it always X and Y only? Okay, sorry, Y and X only? No. You can see in this question, I resolve perpendicular to the beam, to the bar, and parallel to the beam. Because at the end of the day, you must see which is the one that makes sense to you in the question. Because in the case of the moment question, if you don't resolve perpendicular to the bar and parallel to the bar, right, you will have a problem when you need to find the distance to multiply. Okay, so this is the thing to consider and take note of as you go through the question. It's definitely not easy, and this is one of the most difficult things. No matter how many times this has been gone through in school, right, somehow or other you will still be very confused like what to do. But I think most importantly is that when you draw the resolving of force, right, possibly they must be starting from the same point, and then from there you draw like what I did here. So T is T is diagonal, so it's up from that point and left to the point, because this is actually where the force is applied. So you need to also focus on that. Look at where the force is applied, then you draw the arrow from there, and not really to construct a right angle triangle. You should not be doing that. Okay, I hope this video gives you a very good overview of how to resolve forces. There's many possible other examples that we can do these questions, and I cannot complete everything in the short 30 minutes, but this 30 minutes is really meant to help you to recap the way to resolve the forces and how do we tackle a question like that. What do we do first? What do we do next? To give you an idea. But to really understand how to do it, you need a lot more practice, so you can let us know. We can provide some practice for you, or in any case, I think your school should have tutorial. Please go ahead and do them first. And if you still get stuck and you have questions, right, feel free to comment. I'm always available to help you to tackle some of the questions if you need to. Okay, so that will be all for today's lesson. I will be shooting more physics video to help the A-level students coming along, or even the JC1 students who is taking their promo exam. So, and of course, over the September holiday, we will also be organizing a boot camp for the JC1 promo as well as the JC2 physics students. So please call in to inquire, let us know. So we are always able to help you to arrange the class, whether it's online or offline. Okay, thank you very much. Look forward to seeing you in our next video.